We open the hierarchical clustering. Whoa, this is like any sort of clustering we've seen before. That is because this type of clustering is traditionally called a dendrogram. As we can see, it provides a very intuitive view of our data, but what can we say about it at this point? Not much. To get our labels, we go under annotation, where we can get any sort of labels of our attributes. We choose eggs, and we see that it's clustered these true-false values where they landed in this cluster. This isn't very informative. More interesting is perhaps the organism name. Here, it appears that our clustering algorithm has assigned mammalia mostly up top, with some reptiles and perhaps fish. Down below, we may find that there is birds and fish down here. And finally, at the bottom, we walk down and we see that there are insects and invertebrates. However, because we have this hierarchy, we can further walk down a cluster to view interrelationships. For instance, over here we can see that chicken and dove and parakeet are more closer related to perhaps a lark, pheasant, sparrow, and wren than they would to the gull or the vulture or a swan. In this way, the tree can be walked down to study these relationships in detail. We can sub-select the data with either our mouse, as you see me doing, or we can do it with the show cutoff line here and choose a cutoff line for all subclusters to be selected. Though we do not need it in this case for larger data sets, we can also vary the limits here to show to prune the tree down to a reasonable size. This tool visually combines representation nodes but does not affect the underlying clusters. We can then commit this data to send selections to be viewed by widgets further down the pipeline. Finally, the linkage up at the top determines how we link clusters. Orange officially supports 3: single linkage, average linkage, and complete linkage. This reshuffles our classification as we might expect. Single linkage determines the distance between two clusters as the distance between the closest two elements in each cluster. As you can see, this has reshuffled our data set considerably. The average linkage is analogous. It defines a distance based on the average distance of the points in both clusters. Complete linkage uses the distances between the most distal points of each cluster. Now, this clustering is fine and good and rather pretty, but we ought to validate our algorithm a little bit. Luckily, we've already assigned classes based on these biological principles. By selecting type here, we notice that the mammals are mostly clustered at the top, and the fish and amphibian and invertebrate and bird make up the second large cluster, and insects with invertebrates make up the third. Our algorithm had a particular trouble noticing and differentiating between the invertebrates and the amphibians and reptiles, as some mixed in clusters. We leave it as an exercise to pick a better distance metric to differentiate between the two. That concludes our exploration of hierarchical clustering, and we begin linear projections in the next little bit.